Hey, so today we are going to be talking about network security. So this will just be a really basic slash informal introduction into network security because this is sort of the brief introduction. If you want to find out more, you would have to take like a course on cryptography. So this is just the basics of what a user would want if they're sending packets across the internet. What are some basic guarantees and how can we ensure that? Just like a really brief introduction. So let's start off by defining what a user might want when they're sending packets across the internet. So this is node 1 and they're sending a message to node 2, right? And this is their little message packet, whatever you want to call it. So there's 3 guarantees that both users want. Number 1 is confidentiality. What is confidentiality? Oh, I can't spell it. What is it? Basically, if I am sending packets across, I don't want anyone to be able to read it. Either I want them to completely not be able to read it, or I want them to not be able to understand it. So in this case, this usually refers to some sort of encryption, right? You don't want others to be able to read what you wrote, and you can do this by sort of encrypting it, turning what you wrote into a form that nobody else can understand, so that even if there's some, say, malicious node 3 that is, sort of like listening in on your packets when you're sending it across, they won't be able to tell. So confidentiality refers to keeping your message secret / private / encrypted. So, and then number 2, what else do we want to guarantee? We want to guarantee message integrity. So what does this mean? This means that, okay, so we have node 3, they can't really read our secret message because it's encrypted, but what if they add their own gibberish at the end of our message just to mess with us, just to mess with our encryption / decryption algorithm, right? We want to make sure that nobody has been altered our message. Like, we want to ensure that whatever message is being received by node 2 is what has been sent by node 1. No intermediate party has been able to modify it, tamper it, remove it, delete to it, add to it, anything. So message integrity means no modifications. You get the original message. And then number 3, we have authentication. So what does this mean? This means it's the most simple one. Basically, when node 2 receives a message / packet from node 1, we want to make sure that this was actually the one that sent the message. We want to make sure that node 3 isn't just pretending to be node 1 and then sending a packet to node 2, right? We don't want that. We want to make sure that node 1 is genuinely the one who is sending the packet. So authentication, I'll just put down ID, we want to make sure that whoever has sent us the package is actually the one that has sent it and not someone else pretending to be that person. So for this video, we will be focusing on confidentiality. So what is confidentiality? Okay, we defined it. How might we achieve this? So let's draw out this node again. So in cryptography, the sender node is usually named Alice. Sorry for the beeping. And the receiver node is Bob. And Alice wants to send a packet to Bob. And usually the intermediate, the malicious, node 3, the malicious node in the middle is called Trudy, right? And they basically want to violate the 3 things that we just established. Trudy wants to either read our confidential messages, or she wants to modify it, or she wants to pretend that she's Alice, right? So for our scenario, we'll just assume that these are the 3 things that Trudy is trying to violate. So all right. So the way we can get started is, okay, so Alice wants to send a message to Bob, and we established that we want to keep it confidential, and we also established that one way we can do that is by encrypting it. So say her message is ABC, right? She wants to encrypt this. So how can she go about encrypting it? So we can use some already well-defined encryptions. There's DES, which stands for Data Encryption Standard, and it's used somewhat regularly, but it's actually not the most secure because it can be decrypted using brute force. So what's usually used instead is 3DES, which is basically DES run 3 times. So basically you run a message, you encrypt it with DES, and then you use a different key, and then encrypt it again, and then you do it 3 times with 3 different keys, and then you encrypt that. And that is much harder to break. Or you can use AES, which is much more difficult to break. It would take 150 trillion years to break AES, so this is also a very secure key. So for our example, let's look at Caesar cipher. This is not a very, I suppose, secure encryption. It can be brute forced in 26 tries. So basically how this encryption works is that, say you have a message ABC and your key value. So key is like some numeric value which like I guess defines the context that you're using the encryption. Let me just explain. So like say K was equal to 3. So Caesar cipher works by shifting over the letters by a certain K number of times. So if K, our key, is set equal to 3, we would shift over the letter 3 times. So A would shift over 3, so it would be A, B, C, D. So A would become D, B would become E, and C would become F. So this is how Caesar cipher works. Obviously, if you set K equal to anything more than 26, it would loop around, and so the limit for this is set at 26. So obviously not a very secure encryption, but I think it makes things easier to understand if we just think that Caesar cipher is the one that's being used. So let's pretend that, okay, we're going to use Caesar cipher. Alice has her message ABC, and when she encrypts it, it will no longer show up as ABC during the transmission. It will show up as DEF. And when Bob receives it, what does he receive? He receives DEF. And what does Trudy see? She sees DEF. And pretend, once again, that this is a very secure encryption and nobody can break it. So what happens is Trudy has no idea what DEF is, but do you see the problem here? Bob also has no idea what DEF is. And that's because he does not know what this K value is right here. So how do we fix this? So let's assume that, okay, Alice and Bob are friends. They've met up before sending this message, and Alice tells Bob, oh, by the way, we're going to have the key value for our message. We're going to call the key KS, and it's going to be set equal to 3. And Bob says, oh, okay, so I'll set my KS value equal to 3 as well. So when both parties have the same key, KS equal to the same thing, like the same exact key, right, on both sides, this is called symmetric cryptography. And it's because they both have the same key. Oh, I wrote it twice. Right. So now we have another problem, right? What do Alice and Bob represent? They are not really friends, right? In a more real life, oh, sorry, let me go through this first. So now that they've agreed on what the key is, during transmission, DEF, Trudy reads DEF, and now Bob knows that DEF is DEF, and then he knows the key, and he would be able to decrypt it to ABC, and then, oh, he can read the message now. So sorry, going back to the problem, the obvious problem is how Alice and Bob aren't really friends, right? They don't really know each other. How would they have decided on this key before? Like, what if Alice changes her mind and she was like, no, I don't want the key to be 3, I want it to be 4. Or what if Alice has another friend and she wants the key with them to be 5? Like, does she have to keep meeting up these friends? Like, how is she going to tell everyone what the key is? And in a more real world context, Alice and Bob aren't real people, right? Like, this could be like your laptop and Bob could be the DNS server. and you don't really have a pre-established relationship. So what is the workaround for this? So this method involves symmetric cryptography. So the solution for this actually lies in asymmetric cryptography. So I guess just by the name, you can tell that this involves keys that are not the same, because symmetric cryptography is when both keys were the same. This would be when they're not the same. So let's draw Alice and Bob again, right? And she wants to send this message. So, okay. So what's going to be different this time is that Alice and Bob are going to have two separate keys. So Alice is going to have her own keys, KA, and Bob is going to have his own keys, KB. And they're actually going to have two keys. So they're going to have a public key and a private key. So what does that mean? Public key is the key that they would be able to share with anyone without it being a problem at all. So they would be able to share this number across the internet, and this would not matter at all. Anyone can have it. But their private key, on the other hand, is theirs and theirs alone. Oh, sorry, this should be an A. Is theirs and theirs alone. They are not supposed to share with anyone. If so, they would severely compromise the integrity of their system. And yes, so private keys stay private, public keys can be shared. So how does this solve our problem? So what we're going to do is, so the way that the keys are defined is that if you encrypt a message using one of the keys, it can be decrypted using the other key. So for example, if you decrypt a message using the private key, you can, if you encrypt a message using the private key, you can decrypt it using the public key. And the vice versa is also true. If you encrypt it using the public key, you can decrypt it using the private key. So let me walk you through the example first. So what is going to happen before Alice sends this message? Bob is going to send Alice his public key. He's going to send KP, right? And now Alice will have access to his public key. And what she's going to do is she's going to take her message, ABC, right? And she is going to encrypt it using whatever Bob's key is. So she's going to encrypt ABC using that. And she's going to send this new packet, right? This new message. This is M, right? And she's going to send it to Bob. And when Bob receives it, right, he's going to use his private key to decrypt it. And when he does so, he's able to see the message. So what happened to Trudy here? So let's draw Trudy again. She's able to see both of these transactions, right? She has access to Bob's public key and she has access to the message M. But can she decrypt the message? And the answer is no, because this message has already been encrypted using Bob's public key. And this key is specifically designed so that even if anyone has the access, like even if Trudy has access to this public key, she will not be able to figure out the private key. Knowing one key does not give you information about the other key. And that's what makes this unique. So what type of keys would actually fit this? And it's the one that's actually most used. It's called RSA. So how does this work? So let me walk you through actually creating your own public and private keys using RSA. So first, so RSA actually uses two things. It uses exponents and factors, which is what makes it incredibly difficult to decrypt. But let me just walk you through it first. So first, you're going to define two really large prime numbers, P and Q. For example purposes, we're going to choose small numbers just to keep things simple. So you're going to choose two prime numbers, P and Q. For example, let's just say P is 5 and Q is 7. All right, and now you're going to define a variable called n, which is equal to the product of P and Q. So in our case, it would be 5 times 7, which is 35. And then you're going to define a second variable called z, which is equal to p minus 1 times q minus 1. And this is equal to 4 times 6, which is 24. And now we get to the encryption key, or this is part of the encryption key, E. So you're going to define E to be something less than Z, but also have no factors in common with Z. Has no common factors with Z. So basically we have to pick whatever E value that we pick cannot be it has to be less than 24, and it cannot be a factor of 24. So it can't be 4, it can't be 6, it can't be 2, it can't be 12, right? It has to be some other number. Let's just set it equal, let's just set equal to 5. And then we're going to define some variable D, which is our decryption key, such that E times D mod Z, so this would be 5D mod 24 is equal to 1. So when we get to this, you would have to play around with the numbers a little bit, but say D equals 29, right? So we have our E defined here, our D defined here, and our N defined here. And these three components will make up our keys. So our public key, let me just write it up here. So our public key will be defined as 35, 5. And this is what is being sent. So this is, like, assume this is Bob's key, this would be what KB plus is equal to. And then the private key would be 35, 29. So this is the key. But how does this encryption decryption actually work? So to encrypt it, let's see if I have space. Encrypt, you would do whatever message. So our message is ABC. Just assume that there was a way to convert this into a number, and say the numbers were like 1, 2, 3 or something. You would take whatever convert message, and then you would raise it to the e power, and then do mod n. And then this would give you the encrypted message. And then to decrypt it, so this is what Alice is doing when she receives Bob's public key, right? Because she has access to the letter E, which is 5, and then she has access to N, which is 35, right? So, and then when Bob receives the message, right, he's going to take the message that he received, right? This is not the original message, this is the encrypted message, right, when you decrypt it. And he is going to do M and set it equal, and raise it to the power of D, mod N. And that's all. That's how the encryptions work. So yeah, so this is what the public key is doing, and this is what the private key is doing. So why is this difficult to crack? Like I said, as you pick larger and larger prime numbers, it becomes incredibly difficult to do the factorization, right? Which is what you're doing in this step right here. And then also, the other difficult part is the fact that it uses exponents. As you can see here, like, you're raising it to the eth power and the dth power, right? And if you pick bigger and bigger prime numbers, the e will also be bigger, and so will the d. And then, so you're raising it to, like, higher and higher powers, and the prime numbers are harder to factorize. So this makes it a very secure. So yeah, this is how you would ensure confidentiality. There's actually more coming up. This isn't the entire story, because all this being said, RSA is actually very computationally expensive. Just like how the factorizations and the exponents take a lot of time. If you want to send bigger and bigger messages, right, the numbers get really messy really fast. So RSA is not actually used for encrypting messages, but in the following videos we'll see what it actually is used for.